And before I do anything, clear the whole stuff. Otherwise the fun is gone. Edit, clear all outputs. And let's also open LTSpice. And open some noise analysis stuff. Okay, first of all, what does SLiCAP give you for noise components? File, let's say a new schematic, forget about this one for the moment. If you use resistors, they don't have, like in normal Spice, automatically a noise included. So this is just a resistor, but it doesn't have the noise included. If you want to have the noise of the resistor included, because in symbolic analysis, you want to have always the simplest model as possible. Otherwise, your symbolic calculator cannot do anything, or your cannot solve it maybe, or your expressions will be so complex that they are not meaningful at all. You cannot draw any design conclusion from it. So very important for the application of SLiCAP is that we make simple models that only model the thing that we want to investigate at that point. So we are not going to put noise and dynamic behavior and whatever, everything together in one model, because that would result in such a complex expressions that we cannot draw design conclusions. We will teach you in this course how to design things orthogonally. So first design, for example, the noise, and then design the dynamic performance of an amplifier. So while designing the noise performance of an amplifier, we will just assume that the dynamic performance is okay, that we are in the frequency range of interest, we have exactly that transfer that we want. And then later on, if we want to design it and say we don't want to have deviations larger than so and so, we will do the dynamic transfer step by step. And then we don't need to redo the noise, because afterwards the dynamic transfer will be okay. And that was the assumption for the noise. So that's why we do step-by-step design, and you don't want to have everything for the noise included, only what you think is relevant. So let's say I want to make this resistor noisy. The best thing is then to place a current source in parallel with it. And why not a voltage source in series? That is because of modified nodal analysis. Modified nodal analysis is based on nodal analysis, and every voltage source you add will give you an extra variable in the matrix and makes your matrix larger. And inversion of matrices or determination of symbolic matrices, the cofactors from it, is a tedious job. You can do it, and Maxima can do it with very large matrices, but you don't want to wait 20 minutes for if you have 10 symbolic variables and put in the matrix upside down. That is really not nice. So you want to keep your things always simple, and the number of nodes and the dimension of your matrix as small as possible. So here, let's say I call this this resistor, I give it a value R, and then I know that the noise will be, so the noise will be, and it in an expression I always put between curly brackets, 4 times K times T divided by R. And that is the spectral density in amps squared per hertz. And that is what you have to put in here. K and T are known variables by SLiCAP. T is the default set to 300 Kelvin, which is 27 degrees Celsius, and K is Boltzmann constant, which is also known by the circuit. Similar holds for a voltage source. Of course, you can also add voltage noise sources and simply place a voltage source there, and then using the noise attribute here to define its value, and you do it in the same way as I did it here. We also have this later on for offset and bias variations, etc. That is the DC and the DC VAR, and the value standard in SLiCAP is not the DC value, but is the Laplace transform because it is based on the analysis of linear dynamic systems. We have more. We have more noise-related things, but I will want to introduce them later. So we can now build already exercises and do things so that you get familiar with these two, and this will be enough for the moment. So here I created a little example for explaining you the noise capabilities of um, of SLiCAP. Here you see a voltage source with a resistor, a source resistance RS, and the noise modeled. So I didn't use a current because here the information obviously is modeled in voltage, and then I'm not going to change it, of course. So the noise is modeled of this resistor is modeled in this voltage source. And then I will add a resistor in parallel with the signal path RP and assign it its own noise as I did here, 4kT divided by RP amp squared per hertz. And for making it a little bit more funny, I also put the capacitor here, CP, so I can explain you other things as well. This is the output node, and we might want to study, for example, the noise figure of this arrangement, or for example, the total spectrum at the output, the voltage spectrum at the output, or for example, the source referred noise spectral density or RMS value. And that is what I wanted to show you in this next example. I will make it a little bit larger so that I hope that you can all read it. And if not, then I need to put on the chat. So I go to the bottom of the chat if there's any. Will the spectra of the sources be provided during exercises, or should we be able? That is depending on the exercise. I cannot give a general answer to this, of course. So let's hear. We start. This you can download. This is completely available in zip, and there's a lot of comment in it, and I want to go through it step by step. So I have only 20 minutes. I hope it is enough to go through it step by step. So I import everything from SLiCAP. I have a file called noise analysis. I make a project so HTML files will be and directories will all be created. Make netlist I don't do because I have already created one netlist. File name should that be? Yes, file name. But in the I don't use it anyway. In the text in the zip will also be the same error, of course. So you have to change it. Then I create an instruction. I check the circuit here, and you can do Control Enter, and it should result in the start of SLiCAP. And don't worry, this is like some specific thing for my computer. You see here no errors found during the analysis, and I want to create an HTML report as we did everything before. So here you see I have an HTML. Oh, I had to HTML. If I put there HTML, you don't see the HTML, but you see the head. You see, that is also, it was late yesterday evening, so forgive me, there will be a few things probably. Then here is the circuit from LTSpice as imported as SVG. I want to see the netlist just for checking. This is the netlist. You see how it is dealt with, all these parameters. I want to see maybe the elements in the circuit, and you see here indeed that there is a capacitor having a symbolic value CP, no numeric value assigned. And you see for KT divided by RP, it puts it in alphabetic order with capitals first. So that is why it is TK. And only RP is only symbolic. The rest is known by the system, you see. So this you can always check. If everything is numeric, then you can make plots. If it is not, you cannot make a plot because you cannot plot symbolic things. So, and here you see the other components, the V. So undefined components is found with also with params to HTML. You find here, this is defined, T and K is defined, and undefined are CP, RS, and RP. So that is a kind of warning that if you want to do a plot that you are missing something. So now we are going to define the instruction. I want to do symbolic noise analysis, and that requires a gain type. That's important. VI. I'm going to calculate voltages or currents. That's what I'm going to do. So you can execute it. This will do nothing. Only execute will do something. It will execute the instruction. And then I can print, for example, the output noise. So there is a result structure coming back from execute. And this result structure um, has attributes. And one of those attributes is O noise. And here you see if I'm printing this O noise attribute, I will have this expression. Of course, it is much more beautiful to put it on an HTML page. And that is definitely what we are going to do later. But you can also see all the contributions to O noise because there are two sources. This will be two contributions. And here is the Python language syntax for, because it is the O noise terms is a dictionary with keys and values. The keys is the name of the source and the value is the contribution of that source to the output noise. So you can see here, if I do it, I have V1 and I1 contributing to the output, and these are their contributions completely symbolically. If you also define a source, and we did, you see source is V1, then it can also calculate source referred noise, which is called input noise, because this is also called this way in SPICE. It should be source referred noise, which is far more clear than input noise, because input is input of the amplifier, but not the source. But okay, here you have it. And this is the source referred noise of the two contributions. And the expressions look quite complex. That is because I did not standard put simplify in the expressions, because I have found that in some versions of Python, simplify will crash. And I have reported this bug in SymPy and they are working on it. Um, but you can still try to simplify it and make the expressions more simple. That doesn't change them, but makes them more simple. So that's basically what I'm going to do. Here, I'm going to create a HTML page, and you see noise to HTML is a very complete instruction. I put all the result thing of my execution there, and it will make a beautiful page with everything. It means I have the detector referred noise symbolically, I have the source referred noise, and I have all the contributions to either the source referred noise, if there is a source, and the detector referred noise. There must always be a detector, otherwise you cannot do noise. Um, And here is what I show you, because I was looking at this expression and said, well, this is not what I expect. I'm not expecting this. I'm expecting something much more simple, because I know what will be the source referred contribution of V1 and the source referred contribution of I1, and it will not be that complex. It is not even frequency dependent. So what am I looking at? Well, of course, you can try to simplify it yourself. It's not that difficult, because you see this term is exactly equal to this term, so it cancels and only a little bit remains. But if you do simplify, so symbolic Python is standard included in SLiCAP, and it's called SP simplified, and you simplify O noise, you simplify I noise, and you simplify all the terms, and you put them again on a HTML page, then you will see a nice result of that. And you see now the expressions are much more simple, and definitely you see source referred noise doesn't depend on frequency anymore. That was what I expected, and maybe you don't expect it yet because this chapter is very new for you, but that is something maybe you can study and see, because it's not just looking at the expression, it's also understanding them. Let's see if we can do something more. Let's see if we can find a symbolic expression for the detector referred RMS noise over a frequency range from Fmin to Fmax. And there something happens, because what I'm now doing, I'm creating symbolic integration limits. And my also expression also is symbolic. And I'm asking Python to do symbolic integration with symbolic integration limits. And that is not always going in the right way. I could even cancel this because I knew this would happen. I can, remove the try and accept. I'm doing just like making this command and forget about the try, but then I must not indent. And let's do, because I know this will give a problem. Oh, sorry, and I'm running all. Uh, so this will, here's the output, timed out after 5 seconds. Standard, a lot of calculations are not performed by Python, but by Maxima. And that's what you don't even see, because then you have to learn two languages. But let's say under under the skin of this program, there is Maxima asked to solve the integration. And you see it timed out after 5 seconds. I didn't give it much time. You can also say, I want to give it some more time because maybe that is the problem. So then you can set the time limit of Maxima. Sometimes I have really huge problems, and I do uh, uh, ini dot max timeout. I cannot. Okay, but it's in the help file. Oh yeah, here it is. Ini dot, and you see this is all in ini, the initialization. All kind of stuff is initialized before, and here you have maxima timeout. This is set to 5 seconds, and I can make it 600, but I don't want to spend all the time on waiting while I know that it will crash anyway. So it was not able to find the symbolic integral with symbolic limits. So that's why I did it. I gave it a try and an accept, and I composed for you some accept that worked. With the remark already that this is a kind of useless thing. In amplifier design, we never take the integration borders as symbolic variables. We always make them numeric, and then you won't find a problem at all. It will find the numeric integral having everything symbolic except for the integration borders. This is because probably the algorithm in the computer algebra system is different, and I have no influence on that. But you can also say, let's just integrate from 0 to frequency to f. This is ini dot frequency is basically symbolic f, symbol f. Let's just integrate and then substitute the fmax and fmin and subtract this result. That is basically you do the symbolic integration, and here you determine the primitive function, and then you substitute the integration limits into it, and then you do it. So that is much faster. So if I now run this, of course, I have to wait for the 5 seconds because of the timeout, but at the end, it will nicely give me after. So it will print, you see, trying to work around, print, trying to work around. So I know it is doing this exception, and here is the result. And you see what I expected was the arctangent function, and that is really included. So then we can put a nice header on the and do the detector referred noise, a little bit of text, blah blah blah, uh, and um, and here you have then the equation for the symbolically integrated noise. You see there is Fmax, Fmin, and all the parameters of the circuit are still symbolically. And this is the RMS value. So you can substitute whatever you want or find showstoppers, whatever you want, because this expression is easy to handle. If I want to find a noise figure, I also want to have the symbolic expression for the source referred RMS noise contribution only of the source. That is also possible. Or sorry, no, the first thing I do is this was the output noise, is do the source referred noise. And you see here, that's what RMS noise. I'm calculated again, and now input noise over this range. And I try it and I have the same exception, but you will see it doesn't need it because integration here is just multiplication. So it's really quick and can do the job. I can also put the result, of course, on the HTML page. So here you have some text, which is always nice to put there. Um, it is nicer on the HTML page because this is only one sentence. But Jupyter Notebook breaks it in pieces. But anyway, you don't want to have this text in Jupyter Notebook probably. I just do it to create the file. And here you see the source referred noise. And you see if you the RMS noise is just multiplication with the frequency range and taking the square root of it. We can calculate the noise figure. For the noise figure, I must have the total source referred noise and divide it by, and then basically squared, and divide it by the contribution only from the signal source, and then take the log of that if you want. Now, the log of that in symbolic Python is always a natural logarithm. So you have to divide by log 10 to get it a log on 10 based. And what you can see here is as well that my RMS noise instruction here that I used before, RMS noise, has also an argument source. If you default, it is not necessary, it's none. But if you say source is Vn, then it will only do, in this case, the input noise contribution of V1, which is the signal source. And if I put there source, what was it? I1, then it will only do the contribution of I1 to this one. So this is how we can calculate the noise figure, and equation to HTML. Put it all there, and here is your noise figure. You see, and it is as expected. If the impedance in parallel with the signal path goes to infinity, your noise figure goes to 0 dB, because that is log of unity. So then it goes to 0 dB, which means that uh, there's no deterioration of the signal to noise ratio. I want to plot something to show you how you can plot the noise. And here, in order to plot, I must have numeric values. I just took some values, whatever. This
You
can
have a
be.
question in the chat, Anton.
What does star means? Where is that? Oh, sorry. Yeah, that's power. So if you do in Python, if you do 10 to the power of 3, it doesn't understand. It is 10 to the power of 3. That is what this means. Good question, because if you're not used to Python, you can get very confused with it. So here I am having I'm plotting the O noise, the output noise, and in the most simple way. The plot sweep instruction has all kind of automatic features that you don't have to give many arguments. The only thing it wants is, well, this will be the file, and the extension of the file is by default SVG. It is in the INI settings that you can change it to PNG if you want. Then it will generate PNG files, but SVG is better. This is the caption above the title of your figure. This is the complete result of your execution. This is the frequency range, 0.1 kilo sweep scale kilohertz to 100 kilohertz, and this is the number of points, 200 points. Show is true means it's going to show it as well. If you do false, it's not going to show it. So let's do it, and it will make the plot. And here you see the output noise in volt squares per hertz. And I can also do contributions and see the different contributions of the sorry of all the noise sources, you see. And now I have I give much more arguments. I say I want to have all contributions, and I edit on request of you in the latest version of SLiCAP that you can put Y limits, because for your first exercise, people came to me and say, can't I change the range of the Y axis? Well, you can do now. It is just Y lim. And this is, I want to have a range of the axis from 1 to the power of minus 18 to 1 power of minus 16. And this is what I would like to plot here. And then you see the source referred noise, the contribution of V1, and the contribution of I1. So unfortunately, there was a bug yesterday when I was doing this, because if you do the noise sources and you give it a name, say, no, I don't want I1, I only want the contribution of V1, then there was some error in the program still, and I repaired it. So unfortunately, if you want to have the repair, you have to install SLiCAP again. You can just install it over the existing thing. And if you do that, then you have the same picture, but only V1. That can be very useful if you have 20 noise contributions and I say, I only want to see noise contributions larger than so and so at this frequency. Then you have a kind of mask, and you can, from all your noise contributions, say, these are the dominant ones. There's a lot you can do with it. Now, we can also plot the RMS output noise over frequency as a function of the capacitance. That is nice. Now we are going to do analysis you can also do. And therefore, you don't need to step like you would have to do in SPICE. No, we can just make a symbolic expression, including this CP. I'm running out of time. I know this will cost me maybe 2 more minutes to do it. So I'm defining the variables, symbolic variables. And there are two ways. I can do the whole instruction again in a numeric way. I will do that. But I can also use the expression I did before. That was this one. That had everything symbolic in it. And just substitute. And here, I did it because now you see how you can substitute multiple variables in Python. So you make a list, and in the list you have tuples, a tuple of the variable and the thing you want to substitute for it. So here fmin should be 100, fmax 100k, rs 1k, rp 10k, k. Well, I can get it from SLiCAP itself by doing the instruction I1, which is instruction get parameter value of k, and t get the parameter value of t. And now everything is like, say, I have a I have a parameter defined VO noise, which is this output noise in which everything is substituted except CP. So that means I have CP as parameter. So then I'm running this. This makes it simple for the plot routine. So I did it like this. You are running again the instruction, but now with the data type params, and use the result. And then you are going to plot this parameter. So here's again the file name. Here is the title above the plot. Here is the result of the params thing. And you see here the y variable is the parameter I want to plot. And the sweep variable is the one that is left in the expression. That is CP. And I can do a sweep scale nano. So I'm going from 1 to 500 nano, doing units farad. You can make the plot as beautiful as you want. If you do enter, it will give you the detector referred RMS noise over 100 hertz to 100 kilohertz as a function of CP. And it's all in microvolt because the scale, you see, Y scale is micro. This is one way of doing it. Another way is just perform a numeric simulation after deleting the definition of this parameter. If you delete the definition of the parameter, SLiCAP doesn't know it anymore, and maybe I have to change it in the future. So before plotting, you have to redefine it, but give it an arbitrary value, so then it knows it again. So I'm deleting the parameter definition. I'm doing again a noise analysis, and now I set the simulation method to numeric. That's what I did before already. So there will be still CP left in the expression. I define it as a variable and then do exactly the same plot And if you do, this is exactly the same line as the line before, only the file name is different. Otherwise, I'm overwriting the same file and it will give you exactly the same result. If you make CP, however, 0, there will be an error because you cannot divide by 0. And if you look in the arctank expression of the RMS, you will see that CP is in the denominator. But the program doesn't crash on it. It just gives you a warning, like that there is one point in which it couldn't calculate it, but it still plots the whole thing in the same way. So, but to make it beautiful, I just did it like this. Now, then you can put everything on an HTML page, but you have already met the instructions for putting everything on HTML. And probably it will now be a mess because I run many things many times. So if I I restart the whole kernel and do everything again, and you wait for a few seconds because of this. So it's now going to calculate everything, going to the whole script again. Everything, and it is not yet here because you see the star, so I have to be patient, but now it's there and it's here, and then I can go to the noise analysis. Oh, I run it somewhere else, but you can view the HTML file in the result, and you will find everything beautifully typesetted and the figures on the HTML. So you can check yourself doing noise analysis. Maybe it seems complicated, but I think if you study this file, that you really know a lot of the capabilities of noise with SLiCAP that we are going to use later to really find budgets for operational amplifiers, etc., and doing as much as possible of the design automatically.